Okay, today I'm going to do a training session on Rust. Um, it is currently July 29th, 2023. So the Rust current version is, I believe, 1.70, just for reference. So there was a number of things that I wish I knew when I started Rust, and I had to sort of figure out each one myself. Maybe there's other resources out there that I didn't find or didn't look at, but I thought that I would aggregate these together into a simple demonstration of a project that we're going to outline here and build. Um, so some of the items that we're going to cover in this training are variables, basic types, strings, options, results, macros, references, structs, libraries, the mod keyword, implementing functionality on structs, and handling errors with anyhow. There's more stuff. There's lots of other references out there, like the Rust book and many YouTube channels and podcasts to refer to for more in-depth documentation. So my objective here is to efficiently show you how to build a useful tool in Rust. And that's what we're going to do here. I'm going to be leaning heavily on GitHub Copilot because I am also new at Rust, and it is super helpful to have auto completion. So the project that we're going to build today um, is a temperature conversion tool. So it should accept input in JSON format. It should produce output in JSON format, and it should correctly convert between Kelvin, centigrade, and Fahrenheit. Spelling is not my main strength here. Okay, so that's the basic requirements of the project. And to get started with this, I have Visual Studio Code here. We have a few extensions installed that are useful. One is Rust Analyzer, one is GitHub Copilot, Code LLDB, and Genie, which I have hooked up to OpenAI for asking questions like that. So to get started here, I'm going to pop into a terminal in this directory I've created and run cargo init. And that creates a new application package. So the first file I'm going to examine here is Cargo.toml, just to make sure these values are correct. They are. So let's take a look at our main.rs. Currently it's just hello world. So one of the things that I find in programming is that run early, run often. What you want to do is minimize the number of variables, pun intended, that you introduce per change to make sure that what you're doing still works. Now Rust holds your hand with this a lot more than other languages like Python, but still, I'm just going to go ahead and make sure I have everything in order here with cargo run. And there we go, we get hello world. So this is great. So let's take a look here at the project itself. So going back to the cargo.toml file, there's a little bit of package information up here. This would be the name of your package and what Rust edition. Every few years, Rust produces a new edition, and you can lock to a specific edition for backwards compatibility. Version default is just what it is there. As we add dependencies to other crates, they'll be indicated here, and I'll show you that here in a few minutes. The source code of your project, by default, starts in main.rs in a main function. So one of the very first things that I want to show you here about Rust is how to add code in other places in your project. So obviously we have a main function here. I'm going to just give an example function here. And I'll call it up here. So this is the first example. I'll go back to the terminal and run it. Okay, so we got hello world and hello world from foo. This is the first example of moving code out of the main function elsewhere in the same file. So now I'm going to show you how to start using a library within your project to move code to there. So in your directory here, you have your source folder, and in there, I'm going to create a new file called lib.rs. Now you can name this file other things, but if you do, you have to make special entries to Cargo.toml to make that work. And because of that, we're not going to rename it. So I'm going to create a function in here. Okay, now the question becomes, how do I actually access this code from main.rs? And it turns out that your Rust project, basically, you can think of main as producing an executable file, and all of the other files in here are part of the library that is your package. So if we refer back to Cargo.toml, you can see that our package name is this. I believe that Rust will convert that to underscores for how you actually reference that code in lib. So let's take a look here and see if we can call that. Yeah. Okay. So this is the name of the library that is sort of part of and one with your package. It's the crate with that name. We can rename this if we go to our cargo.toml and just want to shorten this to say something like that. We go back over here and call it that. So just wanted to point out that in your cargo.toml, the name of your package is by default the name of the library that is published and not published, accessible within your crate. It would also be the name of the library if you publish it to crates.io. So going back here to main.rs, we're able to call our code there because it's named what it is named here in the package. And I think for convenience, I'll just leave it temp conv1. So you can see here in main.rs, we're able to place code outside of this file, which is a good thing. Now, let me show you how to take that to a couple more levels. So if we go, I'm going to go ahead into here and create a new file called test1. And we're going to say like that. How do we call this code? Let's go back to our main. Okay, so I'm getting an error here in Rust. It says failed to resolve, could not find test1. And the reason for that is, unlike Python, who will automatically discover py files within a directory, Rust does not do that. So if you want test1.rs to be available to your code, you have to go to your top level, which is lib.rs, and just put a pub mod test1. And that instructs Rust to pull that code in and make it available as a test1 module here. So you can refer to it as the name of your library or crate, colon, test1, colon, the name of the function. One of the neat things about Visual Studio Code is if you hit F2, you can rename a function and it will go through your whole source code base and rename it as well. So look over here, it automatically renamed it there. So let's check and see if this is going to run. And there it does, as expected. Okay, so that's just a little bit about how you assemble multiple RS files to work together. I'm going to take it to one more level, and that is directories. So if we wanted to have, say, a larger group of functionality, I'm going to call it test2. You can create a new folder, and in that folder you place a mod.rs. So same way, in lib.rs you still have to say pub mod test2. And then in mod.rs you can put functionality, like you can put a function like that. You can also create other files in test2, like let's just say io.py or rs. And to get this code to be available, you need to put it in mod.rs, same way. So if you have any experience with Python, this should look very familiar because Python uses init.py, Rust uses mod.rs. And you can basically have the same structure that you're used to in Python, just doing it in Rust this way. Again, the only difference being you have to tell it that you have a file there or a directory. So with this I can go back to my main now and say test2, and there's a function in test2, and there's a IO sub module in test2, and they can be called like that. Now, there's a way to shorten these up if you want. Say you wanted to use load file without typing this all out. We could say use it like that, and then just shorten that up to load file. So that's oftentimes handy. Let's see if this works. And there it's working as expected. Okay, so that's a little bit how to structure code in here. So with that, let's delete some of these test files here. And I'm going to create one called io.rs. And I am going to create one called data.rs. Okay, so at this juncture, we have this structure. We have our main.rs, which is our entry point of our application. We have lib.rs, which is the base of our external, or the crate that we're creating, or the library. And this is defining two sub packages, for lack of a better word. I don't know what the correct word is. IO and data. So there's a million ways to structure this. This is more of an example, just so you can see how these pieces might fit together. But in data, we're going to create a couple of structs here. So the reason I'm using the pub keyword is so that the structs are visible from other pieces of the application. If you were just referencing it in the same file, you would not need the pub keyword. So I'm going to create a composite data type here called temperature, oops, temperature input. Okay, and that is going to have a temperature as a floating point number, and then it is also going to have a scale as a, we'll start with just a character. I'm going to name these input temp and input scale. And then lastly, we need to know what output scale we want, like that. Okay, so just as an example here, I've created this struct. I'm going to create a example of it here in the main function here. So let's say let input, or I'll just call it I1 equals so here's an example. Now let's print it to the screen. Okay, so this is a really simple example of defining a struct in Rust, which is your own data type, and then utilizing it in another file here. Let's see if this runs okay. Okay, it was able to print out the input temperature is 32 degrees. Now, I'd like to take the opportunity here to illustrate what calling a macro looks like in Rust. First, here's defining a variable. This is a local variable. And here is how you invoke a macro function. So the exclamation point is the macro invocation operator for Rust. Printline is not a normal function. It is a macro that gets evaluated at compile time, not at runtime. So basically the job of a macro is to take the input here and translate it into other valid Rust code and replace it at compile time. So one of the examples or things to think about here is that Rust does not allow a variable number of arguments to be passed to a function. But yet magically we have a variable number of arguments being passed to a printline function. Well, it's not really a function, it's a macro. So basically this macro is able to evaluate what is sent to it at compile time and then convert that into the correct Rust code to do that work. And then replace this at compile time, and that's what you get out. So anytime you see a macro, you can see it by macro rules here, you need to have an exclamation point. If you do not put an exclamation point, you're going to get this error that says expected a function found a macro, use the exclamation point operator. Macros are super handy, and we're going to see a lot more of them. There's 2 or 3 types of macros in Rust. This is one where you do it inline like a function. There's a couple, there's 1 or 2 more that I'll show you here as we go that have to do with replacing whole chunks of code with other code. But we'll start with this. So here is how you can instantiate a struct. And this is read only because you did not say that it's mutable. If you want to be able to mutate it, you have to put the mute keyword there, in which case you can then say I1 dot output scale equals K. Little side note, notice this is single quotes. That's a char type, which is a single character. It's a specific type for holding a single character. It's not a string of length 1. So it's different than if you use double quotes, unlike other languages like Python. But if I run this, you'll see that the output scale is updated to K because I made that mutable. Mutation in Rust is something that you don't need as often as you might think, and you'll be seeing that as we go along here. Okay, so I've managed to create a sample temperature input here. Now, I think that the next thing that I want to illustrate to you guys is a better way than using F and C. So let's investigate that. Let's go over to our data here and say, well, you could put F, C, or K there. First of all, they're abbreviations, which can be confusing. Secondly, what if someone puts A, B, or C in there? then you have to have code to handle all these other possibilities. So Rust presents a much better way of doing that, and that's called enums. Enums are fantastic. But at the most basic example, the most basic level in enum is a type that has either 1, 2, or it has either this value, or this value. It cannot have more than 1, and it cannot have 0. It has to be equal to one of these exactly. There's a lot more capabilities that enums have that we can go over later, like attaching values to them, which is fantastically powerful for representing the state at any given point of a specific system. But the way this is, if we have a scale enum that has to either be Celsius, Fahrenheit, or Kelvin, then if we use that instead of char here, our temperature input structure is always valid now. It cannot have any valid conditions, because as long as you have a floating point number and you have an input scale and an output scale, you can do the conversion. I'm excluding issues like not a number and other odds and ends like that for the moment, just for simplicity. But this is a much better way to represent this data. So let's move back over to where we're using this and see what the problem is. Well, the scale is, the struct is now expecting scale, but we're passing a char, so we need to fix that. And to fix that, I'm going to do a little bit of a use statement here. And by doing that, I can shorten these up a lot. And then down here, I can say scale Fahrenheit, scale Celsius. So that is the way that you import or use other functionality from other libraries, files, crates, etc. However, if you want to use more than one thing, at a time, you can use the brace syntax like that. I'm actually not sure what happens if you attempt to do it this way. Might as well try and see here. If I run cargo format on this, it didn't complain. So that's another valid way of doing it. Depends which is clear to read, I guess. Okay, so we're getting a complaint here. What's the error? Scale does not implement the display trait. Oh, traits. They are a huge, huge capability in Rust. And without getting off the beaten path here, let me show you an example of this. If we're going to print this out, now input temp is a float, which does implement the display trait. Output scale is our own custom type. It's an enum, so it does not implement any extra code in your program to do any printing unless you tell it to. So that's one thing about Rust. Like, unlike Python that has all of the code there to do all of the things, Rust is not going to automatically create code or have code to even do something simple like print out an enum unless you specifically have it add that code. So I'm going to show you how to add the display trait to our enum up here. So I'll say okay. So this is the mechanism by which you implement a trait on a type in Rust. It uses the impl keyword, and we're saying that we're going to implement this trait for this type right here. Now, where the trait is defined in Rust, or whatever library defines this, the format module, defines this trait as meaning that if you implement this trait, you have to implement a function called fmt, which accepts these two arguments and returns a format result. So basically, that is the pattern that this trait requires to be implemented. And it's fairly simple. Self is a reference to the scale, and the formatter is something that you can use to do the formatting with. And then they use the, to simplify our life a little bit, they use the write macro to write this text into the formatter F. You can see this is called F. I'm going to rename this just for clarity. Formatter. So you can see that we're using the write macro to simplify the process of writing text into that. So by implementing this trait for this type, we can now notice that the error has gone here. So let's try running it and see what happens. Okay, notice it used C still, however, it actually got that because it ran this code. This is a good time to introduce the match keyword too, or match expression. Match is a fantastically powerful feature in Rust, which allows you to match an expression against these different things. So since self is a reference to the, since self is, the type of self is an enum scale, then it has to be equal to one of these three values. If I remove one of these, we immediately get an error in Rust saying, hey, you didn't take care of Kelvin. That's not cool. Rust will not compile this code because there's an option missing here. And likewise, if you went up here and added another temperature scale, it's going to come up here and notice that you missed that as well. So even if this was in completely different parts of your program, if you make one small change here, the compiler's got your back. And it's not going to let you introduce a simple logic bug like that because you forgot to check one of the match items. So there's another trait and another way of printing this stuff out, which I'm going to show you here. So that's the debugging formatting. Okay, so I'm going to go delete this implementation here. Now the colon question mark, the colon lets you put a format specification there, and the question mark format specification is for debugging output. Now, floating point numbers, F32, have a debugging output, but our custom enum does not have a debugging output. So, and likewise, if I wanted to print the whole struct out, it's going to complain as well because it does not have a debug trait implemented. So let's go back and implement the debug trait for both of them. We'll let Copilot do the hard work here. Okay, so debug is similar to display, except it's for debugging information. So for the scale enum, we've implemented debug to print out Celsius, Fahrenheit, or Kelvin. And then for the temperature input struct, we've implemented debug to print out just this, just a developer readable display of this information. And that cleared up the errors. No more errors. It's able to print these out. Let's see what it looks like when we run it. You can see that there's how it prints out the enum now. And here's how it prints out the whole struct, which is great. The problem about that is that it's not great to have to type this kind of code every time you want to print something out. And this is where macros come in again. So I am going to annotate this with a macro called derive debug. And I am going to delete this. And that is functionally the same exact thing. Because the derive macro. This is a macro, and it applies to the whole following block here. It doesn't just apply like a function call. It's literally applies to this whole chunk. And what it's doing is it's able to rewrite this code or add to it. So when you say derive debug, it's the exact equivalent internally of that. It literally rewrites this to append an implementation of the debugging output. But it's a whole lot shorter. Now you still have the capability of doing it yourself, if you wish, but most of the time for debugging output, it's super easy to just let it auto-generate that code internally. And same here with this struct. I can just say derive debug, get rid of the debugging implementation, and my whole file is reduced down to that, which is awesome. Let's see if that works as well. Indeed it does, and it even looks the same. Okay, so we have covered, if we go back to our README, we started to cover quite a few things here, calling macros this way, calling macros this way, libraries, and mod. We've covered variables. We've covered how to implement traits, structs. Yeah, so we're getting there. Okay, so if we go back to the objective of our program is to accept input in JSON format, produce output in JSON format, correctly convert between Kelvin, centigrade, and Fahrenheit. So let's finish the conversion first and then worry about the input and output. So if we go to data, we have a scale, we have a temperature input, we need a temperature output struct as well. Okay, so we're going to output the temp and the scale. Great. Now we have a temperature output. Okay, so now we are going to need code to do the conversion. Now we can do that a few different ways. We could put the code in here by implementing it on this struct, or we could make a separate function for it. I'm going to go the direction of making a separate function for it. Okay, so we need to convert a temperature. We need a temp input. I'll just call it temp as a temperature input. I'm going to make that a reference. We'll get to that a little later. And it's going to return a temperature output. And it's immediately complaining here. Mismatch types, expected temperature output found, empty parentheses. That's called a unit type in Rust, and this is equivalent to saying returning the unit type. If you don't return anything, or if you have an empty function or nothing after the last statement, it returns a unit type automatically. Now Rust by default returns the last expression. So it's also equivalent to that. That is the last expression. But what Rust really wants us to do is to say, I'm just going to hard code one here for the moment. I don't even have to define a variable. I can just put it right there at the end without a semicolon at the end because it has to be last. And there we go. It's going to return that. Okay. So we have to do we can get back to that in a minute. Let's go to main and make sure we're calling this correctly. Okay, so we got an input temperature. Let's convert this now. call it O1. Okay, this is how you call a function. I illustrated this earlier. It's in the temp conversion 1 library, data module, convert temp function, and I'm passing a reference to the I1 value here. It's important to note in Rust that every value has one and exactly one owner at all times. So at the time that you create this value, its owner is assigned to this variable. And if I were to pass, let me give you an illustration of how to do this wrong. So let's say we're not using reference types. I'm going to just say we're going to take a temperature input, and down here we're going to pass I1, just like you would in another language. And that works fine. Let's print input. Okay. So here's our input struct and our output struct. If I try to run this, you can see an error there already. It's going to completely fail because it says, oh, that's just a warning because we didn't use that variable. But the real error comes down here, borrow of moved value I1. It says value borrowed here after move. Okay, what in the world does this mean? Well, let me explain it. So we created a value here, and the ownership of this was assigned to this variable. When we called this function and passed this variable to it, the ownership of that value got transferred to this variable here. And this variable dies at the end of this function. It's local. And the ownership of the value dies with it, and it goes out of scope. Rust cleans that up right there. So this is kind of interesting because we created a variable here. In other languages, you'd think, well, I passed the variable here and then I can use it here. That's not how it works in Rust because the ownership was moved. So the way around that is just two ways around that. One is that we could say we could clone it and literally pass a copy of it. Except our struct does not support clone. That's funny. Let me fix that real quick. Yeah, we have to even tell it to create code to copy itself. Okay, so now we've added code to these types to copy themselves. And we're going to go back over here and see, because I sent a copy of this, then we can still access our original value. That is not the right way to do it, just to be clear. There are times that you need to copy values. Like if you need to store them in two places, you can't have the ownership held by two things at the same time. So there are times that you need to clone values, but they're fairly rare. There's a much better way of doing this. I'm going to go back and remove clone from these. And the way is to create a reference and send the reference along. So I am going to create a reference here. And I'm going to go over here and tell it that we're expecting a reference type. Now, the way this works at this point is that instead of passing the ownership of the value to this function, we're creating a reference to this and passing that to the function with the condition that there may be some limitations on how you can use this in the meantime, but this is a single-threaded program and there is no meantime. So by the time you get to your next line of code, the reference will have been destroyed anyway because it's expired. That function's over, it's not used anymore. And you can go ahead and continue using your original value. Since this is not mutable, you could continue to do it anyway. But if it was mutable, there would be more tight restrictions about that. But this is the way to pass a reference to a function, and that is vastly superior in almost every way to cloning. Most other languages clone like crazy. When you call functions, it clones. When you do a lot of operations, like in Python, whenever you add a modified string, it creates a new copy of the string, and they achieve a lot of safety in the language by not letting you change a lot of values. But in Rust, this is called borrowing, and it's really borrowing the ownership through a reference is probably a good way of describing that, because the ownership is temporarily moved to the reference and then it comes back. So let's see how this works here. We still have our warning, we'll get that in a minute, but you can see here's our input struct and here's our sample output struct. So we have input and output working. And I'd like to point out again that what I'm doing here in the programming is creating a structure to build our program rather than trying to jump into all the details at first. But now that we have the structure working, let's jump into a couple of details. So let's just go to our data.rs. I don't like the word data.rs. That's fine. I'll leave it what it is for now. But let's do the actual conversion here. So we're going to say let output equals match. There's a lot of ways to do this. Okay, one way to do it is that you could match to see which input scale we're doing and then have a separate function for each conversion. That would be one way. I don't really like that way. Another way would be to say, let's match the temperature itself. Let's see what Copilot comes up with here. Here we go. That is extremely verbose. It's hard to even tell what it's doing here. Okay. It's saying, it's going to say, okay. If this match will match only if the input scale is Celsius and the output scale is Celsius. So this is sort of an advanced match that matches on all these fields in the struct to see which one matches. And it is pretty verbose because you have everything labeled, and it goes down through all these different possibilities. And yeah, Copilot put the calculations in here, but that is extremely difficult to read. So I'm going to suggest a simpler way here using a tuple. And you know, I don't actually even need to set that to a variable. I can just put my match, get rid of my parenthesis or my semicolon at the end, and the result of this wait a second here. Sorry. Okay. I got to clarify my objectives here. I got myself confused for a moment. So we're returning not just a temperature, we're returning a temperature output struct. So we need to either update each of these to return the correct struct or put that at the bottom. And I think that we can probably put that at the bottom. So we're going to say let output temp equals match. Okay. And it's saying, it's already catching us. It's saying missing match arm, Celsius, Celsius, Fahrenheit, Fahrenheit, Kelvin, Kelvin are not covered. Because Copilot didn't see that we needed that. We could do a wildcard match and say that if they're the same, I mean, if any of the remaining ones, the temperature doesn't change, but I think I would prefer to be very specific about it, like this. So this gives us all of our possibilities. So you can see here, we're matching a tuple, so that's two values. And if those two values are these two, then here's the formula. If those two values are these two, then here's the formula. And it goes on down through, et cetera, et cetera. And it covers all the possibilities. And our objective is to return a temperature output struct, which is these two values. So let's go ahead and do that. We'll say okay, here's one of these ownership issues here. It says cannot move out temp.output scale, which is behind a shared reference. That's an error that you get from time to time. And what this means is, notice we're taking a reference to temperature input struct, and we're returning a temperature output struct. And what I'm attempting to do is use one of the values from the input temperature as part of the output struct. And if you think about the way memory is allocated in the computer, there's a chunk of memory for the input temperature struct. And I'm being like, hey, I want to use one of these pieces for the output struct. And Rust is like, hey, it's being used over here already. You can't take it. You can't just grab it out of there. So this is where cloning is actually very valuable. And for that reason, I'm going to go ahead and implement clone on this scale. And down here, I'm going to go ahead and clone it so that we return a copy of that for our output argument. Notice there's no return argument or no return statement. I could put return, but most people programming Rust don't put return. They just make it the last thing here. And there's the implementation of our temperature converter. So just to review, I'm going to rename this to input temp, just for clarity. We're expecting a reference to a temperature input struct, which is this. And we're going to return a temperature output struct, which is this. So all the struct definitions and all the logic processing and everything happen in this one file here. Let's go look at how it works in main. So we're doing the conversion, 32 Fahrenheit to Celsius. So theoretically, the output should be what, 0? There it is. Output temperature 0 Celsius. Okay, so if it was a live audience, I'd say, is there any questions? But there's nobody to talk back to me right now. So just to review this one more time, we have an enumeration, an enum, with 3 possible values. We're utilizing that in our own custom data type called temperature input, using it twice here. And then our temperature output is using it again. Now, what we need to do is to produce this as JSON. We need to read JSON in and write JSON out. So let us go over to our IO file and write a function to open a file. Okay, so this is basically how you would implement a function to read a file. I think for simplicity, I'm going to get rid of this code here. I'm just going to put it in the main function. I'm going to delete io.rs, get it out of lib. I'm going to rename data to temp. Even renaming that file, it seamlessly handled everything. You can see here it renamed that to temp.conv. That's probably an unnecessary level of abstraction, but I'm not worrying about that for this example. I could add convert temp here and get rid of this extra length here. But let's go ahead and do the dirty work. In order to read JSON in and write JSON out, we need to use the serde library. And the serde library is an awesome library. Suggest you look it up and read about it. But let me show you where that needs added to make use of it. In Cargo.toml, under dependencies, we need to add a dependency for serde. So I am going to just go to my terminal here and say cargo add I want to add a dependency with the derive feature because that's one of the features that serde offers. Of the 6 features that they offer, I just turned on, I think this was default, and I turned on these ones. And the effect of that is that in my cargo.toml, it looked up the latest version of serde and added this features definition to it. If we want to handle JSON specifically, we have to add one more. Like that. And I believe we don't need any of these extras. So there we have serde JSON. And let's see what we need to implement this. Now, the way serde works is mostly using macros like this. So let's say use serde serialize, deserialize. So these are 2 macros that we're bringing into scope here, and I'm going to derive them as well. There. And then temperature input we only need to deserialize because we're only reading it in. And temperature output we only need to serialize because we're only writing it out. And this one, the scale we need to serialize and deserialize because it's utilized by both of these. If I were to remove this from this dependent enum, we would immediately get errors that are very confusing. Trait bounds not satisfied. Very not a clear error, but if you see that, there's a good chance that you're missing a dependency on serialize or deserialize. Pay attention to whether your code base shows up as red or not whenever you make a change, because that gives you a hint real quick to what caused it to happen. So, okay, so we've implemented serialization and deserialization because serde, the library, is actually adding code to these structs to specifically read them in from the JSON format now, or from any format, but it's using the serde JSON, it'll be able to handle it with the JSON format. That's the first step to doing the serialization and deserialization. Now, let's say we need to create a file here. Let's see, I'm going to create a new file called input.json. And we need to I'm going to use Genie here. Say convert this Rust struct generate valid JSON to use as sample input for There we go. I can just copy that now and go over to input.json and paste it. It's easier than typing it. Okay, so here's some valid input data. So let's think about how we're going to actually implement this software. First thing that we want to do is open input.json and deserialize it to a temperature input struct. Okay, so first of all, we're going to open it. Then we're going to deserialize it. And now we're going to convert it. We're going to serialize it again. And we're going to write it out. I'm going to write it to the terminal. Okay. So let's walk down through this. We're not needing scale here anymore, so I'll remove that. Before I walk down through it, let's make sure it runs. Oops, didn't need to do that. Cargo run. It's going to take a moment because it had to compile these other libraries, but that's just the first time. Okay, so we're getting a panic here. No such file or directory. Interesting. Reason being, I put my input.json in the wrong directory for some reason. Okay, let's try it again now. There we go. Output temp, output scale. Let's walk down through how this works. Because you see, once you get your structures in place, everything else just falls right into place. No problem at all. But let me walk down through this here. So we're going to create a input file, which is a standard file system file type from this path. I'm going to get the unwrap here in a minute, but just say that you don't want to use unwrap in production code, almost never. But it's necessary for a reason I'll explain here in a minute. This is going to open the file and give us a reference to that open file called input file. And now our input data, how does serde know what to deserialize it into? And what it knows is that we told it the type of this variable is temperature input. I don't know if you can see on the video here, but this file, that word is not there. The editor's automatically placing that there, but this word actually is here, because if we didn't put that there, serde would not know I'm not sure how it figured that one out. Oh, yeah, wow. That's pretty clever. Okay, the reason it knows it's a temperature input is because we used it down here as an input temperature. So Rust compiler backtracked that. It said, well, you're using it here as an input temperature type, so therefore it must be a temperature input type. Therefore, serde knows it's a temperature input type. That's pretty awesome. So that's what serde, once it has the type, and remember the type is this type here, temperature input, the struct. Once serde has that type, it knows how to deserialize it into that structure. Once we have the struct, we just pass it to our convert temp function, pass a reference to it, that is, and then we get the output, which is a temperature output struct, and we use serde to serialize that to a string, and then we print it out. So this is the implementation complete. I think I'll defer error handling to another talk here because it's been about an hour, and I think this is a good place to start. Well, yeah, no, yeah. Anybody want to vote? Go over error handling now? Not go over error handling now? Okay, let's go over error handling now while we're on a roll. So what is unwrap doing? This is a can of worms that's super important to understand, but I'm going to remove it and see what happens here. Notice the type here immediately changed to result. Okay, result is a enum that looks like this. It has two possible values. One is okay, and the other one is error. And these hold one value each. So OK holds a variable of type t, that's the t, and error holds a variable of the type e, and that's the e. This is called generics. Kind of complicated, but let me illustrate it here for a second. So I'm just going to go up here and say let r equals result Okay, sorry about that. So this is a result enum. I'm going to call it my result. And I'm specifically giving it a type. So the result, the type is a result enum, but the OK type is a string and the error type is a string. And what that gets passed, if you recall, if I go to the definition here, here's the two parameters that get passed to the type. And T is used as the OK type and E is used as the error type. So in this particular case, I'm saying my result is equal to an OK result. And I'm going to show you an example of error. Okay, so we have my OK result and my error result. So you can see that even though it's the same type, which is result, enum, the one is OK value and the other one is an error value. And we can use match to extract that. We can say, notice if we match my OK result, it's going to match the OK arm. This is shorthand for saying result OK and result error. And it's going to extract that value out of it and assign it to S, and then we're able to access that there. So if I actually ran this, let's do it with the error result. Okay. I'm just going to put a return here, which is going to give me a big warning. But let's see what this runs. Okay, so my OK result see how it's okay, hello, and the error result is error bad. So that is because we defined my OK result as being the OK variant of the enum, and my error result is the error variant of the enum. Now this is super important in Rust, because any operation in Rust that might fail, like opening a file, what unwrap does is just gets the OK value right out of that. But the problem is, if you don't have an OK value, if you actually have an error value, it's going to panic, and your program ends instantly. As you guys could see, when the file was named wrong, I'll just rename the file here. I'll just call it JSON2, and we'll run the software. We're going to see a panic. It says it got an error value on unwrap, and there's no such file or directory. That is obviously not desirable behavior during production software. So for quick and dirty stuff, that's fine. That's not going to go into production. But otherwise, that's not good. So let's take a look at the proper way of doing this. And you'll notice the type of input file is file because we unwrapped it. But if we take the unwrap off, suddenly the type is result. So it could be either an error or an OK. We need to check that. So we're going to have to use match keyword here. So we're going to match it. And we're going to say if we match the OK variant, we're going to have a file and we'll return that file. If we match the error variant, we're going to panic and end the program with problem opening the file. Let's see what happens when we run that. Okay, here we got our own message coming up. Problem opening the file. No such file directory. So that's a little bit better. It's not always clear what you want to do when you have an error like that, but usually in this case we can't go forward, so we have to stop. I could also put a return in here. Or I could put a block of code that says, say, for example, we'll print an error message out, and then oops, and then we're just going to return. That would be similar to panicking. So let's see how that looks when we run it. Our problem opening the file. So that's sort of a way of more manually handling it. I'm going to rename the file back so that we don't have that error now. And we have to do the same thing here. What if we have a problem with the JSON data itself? So we have to match this. If the deserialization, meaning if reading the JSON into our data structure fails, we'll get an error back, and we'll print that out and return. Otherwise, we will say, okay, we're going to use the data. Because remember, the result enum, okay, holds a value, and we're extracting it right here. And error also holds a value, and we're extracting it here. So that's, if I were to continue this, I would need to do that one more place here. And that's for serialization. Let's say you tried to serialize a value that wasn't serializable. You'd get an error. Okay, let's try this with our new and improved error handling and see what happens. Okay, it worked. Let's violate the input data. We'll put an invalid input scale. Problem reading the file. Unknown variant Celsius X, expected one of, da 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 da. column 3, line 29, or line 3, column 29, line 3, column 29. Yeah, right there. So that catches the errors, and that is a super critical thing in Rust, is that it's not going to just return a value if it can't. It's going to, if you have anything that's optional, use an option enum that has some and none. Some wraps the value that you're interested in, none doesn't wrap any value. If you have an operation that might fail, you use result, and you have to check the response. And this is one of the things that gives Rust such incredible reliability. It does not leave any of these things to chance. So there are ways to improve on this. The anyhow crate is one of those ways. Let's add it to our package here. So I'm going to go to my cargo add anyhow. Okay, we've added anyhow. So if I look at my cargo.toml, you'll see it got added here, latest version. Now, I am going to do a little adjustment here to my main. I'm going to tell it I want to return an anyhow result. And I'm not really particularly interested in returning anything right now, so I'm just going to use the unit type. And at the end here, I have to return OK. In fact, these are all giving me errors now because they're not returning results. I would have to return errors and all that. But I'm going to eliminate, well, I won't eliminate this. Anyhow offers a nice, convenient macro for this. It's called anyhow bail, and it's like a panic except with a little bit better formatting and some other features. So all I've done at this point is added the anyhow library and told it that I want to return an anyhow result from my main function. Let's run it and make sure that still runs. Still runs. Let's introduce an error again. I'm going to make an invalid piece of JSON here. We'll run it again. Okay, so this is an anyhow bail generating this, which is fine. We still have too much code though. I don't like writing this much code for error handling everywhere we go. So let's figure out how to shorten this up. And I'm going to introduce the question mark operator. Okay. Now that you've seen how you have to match it manually, check for OK, check for error, you see the disadvantages of using unwrap because that causes a panic. Oh, unwrap just extracts the OK value, but it panics if you have an error value. This is where the question mark operator comes in. And now, notice how this is returning a result. However, if I put a question mark here, now it's returning a file like you want it to. What does the question mark do? Well, the question mark decides whether the operator should produce a value or propagate it back to the caller. What that means, candidly, is that if it gets an OK value, it's going to just give you the OK value, the value contained within OK. If it gets an error value, it's going to literally return that error with a return statement. So it's going to say literally return error. I'm sorry, return. That's the basic idea. that the question mark here, I'll show you the two examples. This is the short version because what the question mark is doing is basically this. It's matching the output, and if the output's okay, it just extracts that okay value and returns it to you to use here. If the result is an error, it literally returns that error up and out. So this allows you to propagate errors. So let me simplify this code down now to use the question mark. Very simple there. Serialization as well. I can just get rid of all of this. Get rid of the match. And we are back down to this simple version. Let's see if it runs. We should get an error. Error, expected value at line 2, column 19. Okay, that error is nice and clean. Got a simple error coming out here. However, it's not very helpful. We don't know what's going on, where it came from. I'm going to guess it came from the conversion here. But this is where the anyhow library starts to shine, because before you put the question mark, you can use anyhow context, and that gives you the ability to do this. Dot with context. Deserialization. Okay, so what I'm doing is providing context to the error. So if you think about the flow here, this function returns a result. If the result is okay, with context does nothing to it. If the result is an error, with context wraps that error with additional context that it gets from here and returns that. You may ask, what's the syntax? That's a lambda function equivalent for Python. It's like a closure. These are the arguments here. There's no arguments, and that's the function body. And the reason they do that is because you might not know the context until runtime. So this lets you generate the context at runtime. There's an alternate version of this, which is just context, and you can pass a static context to it, like that. And then you put the question mark after that. Now, let's see if this helps us at all when we run it. Error, while deserializing input.json caused by expected value at line 2, column 19. Now that starts to make a lot more sense because we know where the error happened, because we added that context. So this is how you can use anyhow to propagate errors up properly. Let me show you one more example of how anyhow might work here. I'm going to fix input.json. Let's say it's minus 10 Kelvin. Okay? That's not a valid temperature. So let's make our conversion function raise an error here. So we'll go to our temp conversion. Look at our conversion temp. Okay, so we're going to say, first of all, we're going to return anyhow result of a temperature output. So this function is going to be upgraded to returning okay or error. We can return okay, like that. To get that to work, we have to pop over here. Now, notice how it's returning a result. We have to extract that with a question mark. Let's make sure that still runs. Okay, still runs. We're getting an invalid Fahrenheit because it's too low. It's not a valid temperature. So let's make our function capable of failing. That's what we're trying to do here. Now that we've put the framework in to allow it to fail, let's put a validation step in here. There's actually a shorter way of doing it. Well, that's fine. So you can see here, we're going to match the input scale, and then we're going to check if the input temperature for each scale is too low. We're going to return an error immediately. So this is this is a way that we're returning error here in the case of an error, but down here we're returning OK and wrapping the OK value. So the error wraps an error message. This is a way of generating an anyhow error conveniently. So there's probably a shorter way of doing this. Let me show you maybe a way of doing this. If I say if let too low equals, and then I'm going to say if anyhow bail. Okay, so we can simplify this down by saying we're going to actually just return an expression. Okay, so what we're doing here is we're defining a too low variable to be equal to the result of this match, which is simply, keep in mind, a less than is a Boolean operation. It's going to return true or false based on the comparison. It's going to return true if the temperature is lower than that. This is going to return true if the temperature is lower than that. This is going to return true if the temperature is lower than that. Goes into here, and then we're going to check it here. We could even shorten this up further by saying if match, then do that. Just make it all one. Not even have a variable. So we've taken something that was pretty verbose and we've reduced it down to something that's pretty short. I want to take the opportunity to show you cargo format here. I'm going to say cargo. Well, let me do a get add. Okay. Now cargo format, it reformats your code. And in this case, you can see it took this long. It actually reordered these imports to put them in alphabetical order. And then it took this really long line of code and put it into 2 lines. And same kind of thing down here. So if we look at main, you can see it just cleaned up our code for us. Notice it's now fitting on my screen without wrapping. Let's see if it runs. Okay. Error, temperature is below absolute 0. Now, might be nice to know what the temperature actually is. Let's just make that little temperature doesn't implement display. We'll use the debug. I'm going to run cargo format again because that was a long line, and we'll run it again. Okay, temperature minus 10 Kelvin is below absolute 0. So no good there. Let's make it 0 and see what it says, because that should work. There we go. That worked. So just to review, we had to modify our main function to expect an anyhow result type. And then we can use our question mark. If we didn't do that, it would complain everywhere and say it can only be used with a function that returns result. Um, it's actually, just to dig in a little deeper, it's the from residual trait, which means that you can actually implement support for question mark on your own types if you really wanted to. It's an advanced feature, but that's how it's done. Instead of them hard coding it into option or any of the results or options, they actually based it on having this from residual trait. So you could implement it yourself in your own libraries if you needed to. Now there's two main error handling libraries that Rust community uses. One is called anyhow. That's what we're using here. And anyhow is probably best for command line software, like what we're building. The other one is called thiserror. And thiserror takes a much more structured approach to errors. It expects you to know every possible type of error that you're going to get and what to do with it. So the basic way to delineate the two is to say that anyhow is useful if you want to handle errors gracefully, but you don't care what the error was. Thiserror is useful if you want to do something different based on what error came back to you. So say you're on you know, say you wanted to open a file, and if you got a error of a specific type, you wanted to create the file. Maybe the file's missing. Create it. Thiserror may be a better match for that. If you want to handle web errors, like a file not found, you might want to return a 404 error. Thiserror is probably better for that kind of thing. But this is an example of how to use reading files, defining variables, serialization, deserialization, serde, anyhow, printing, macros, structs, enums, derive, using these types of macros, and using the match. There's probably some other things in there too. But match is fantastically powerful, and it allows for super clean code. So everybody, that's the conclusion of this training. Till next time. Thank you.